All right, so this is perhaps the most important chapter of the year in that it brings everything together, everything we've been working at. Most whys, if you ever had a why in this class, most whys will be answered in this chapter. Between this chapter and the next, most whys will be answered. Okay, called chemical bonding, and as you can imagine, it explains why atoms come together to form compounds. What most affects the physical and chemical properties of atoms? How they're bound together. How they're bound together. For example, carbon is extraordinary. You have carbon bound together forming sheets in these little ringlets. And those sheets will be able to slide past each other, creating a substance that is so soft that it's used as a lubricant. It is graphite. It's what is in your pencils. Now, it's not, what's in your pencils is not pure graphite. Because if it was, then when you went to press it down, it would just kind of create a little puddle. It's that soft. So what they have to do is add what? Does anyone remember? Yes. No. Graphite is carbon. No, that's poisonous. You don't want a kid sticking the pencil in his mouth if it's lead in there. There you go. That explains a lot. Clay. So the more clay they add, the lighter the mark it's going to leave behind. So a lot of artists will use special pencils. Most of the time we use number 2 pencils, but they'll use number 3s and 4s and 5s and maybe even number 1. The last time you used number 1, you were little bitty. Number 1 has a lot of graphite, not as much clay, so it's softer. So when the little hand presses down, it creates a sufficiently dark mark. Because when you have a little hand, right, they don't have a lot of strength. They can't bear down. So you use number 1 pencils when you're little. But when you get to have enough hand strength, then you're allowed to use a number 2. And the number 2 usually is dark enough. If you want lighter, you go with number 3s and 4s and 5s. But that's just for artists. But isn't that amazing that carbon, charcoal, if it forms these little ringlets, is super soft. And yet, if it forms these tetragons, and we're going to look at them here in a second, tetragons, then things are very different. Then you create this beautiful, clear crystal with many facets that can only be, it's so hard that it can only be cut with a chisel, that it itself is made up of the same substance. You have to be an expert in order to chisel it, in order to create the proper facets and designs that people would want to buy and put it on a golden ring and then get down on one knee and propose. So we're talking a diamond ring. Isn't that weird? A diamond and your pencil lead are the same thing. The difference is how the atoms are arranged. And we have come up with the technology to even change those 2 forms. They're called buckyballs and fullerenes and nanotubes.
In this video, we are going to learn about the structures of buckyballs, also known as Buckminster Fullerenes, graphene and nanotubes, and what their importance are in an area of science called nanoscience. You may already be familiar with diamond and graphite as 2 allotropes of carbon. Allotropes are structurally different forms of an element. There's a video on this channel called Giant Chemical Structures that you might want to look at. If you have watched this video, can you remember the structural arrangement of the carbon atoms in graphite? Pause the video and resume when ready. The answer is that graphite exists as sheets of carbon atoms arranged in hexagonal rings. Fullerenes are carbon-based molecules with a hollow cage-like structure. Robert Curl, Harold Kroto and Richard Smalley discovered the most common fullerene in 1985, the Buckminster Fullerene. It consists of molecules containing 60 carbon atoms joined together forming a hollow sphere. There is an alternating arrangement of hexagons and pentagons, much like that seen in a football. Can you think why the space inside the fullerene is of importance? Pause the video and continue when you have a suggestion. The answer is, the space is big enough for atoms and molecules to fit inside. Already, scientists are utilising this to cage radioactive metal atoms and drugs. In one potential drug therapy, buckyballs containing cancer drugs are coated with a chemical that causes them to gather around cancerous cells. Once there, they deliver their drugs without harming healthy cells. Graphene is very similar to graphite, except there are no intermolecular forces holding the hexagonal arrangements of carbon atoms together. It has a two-dimensional structure. It has some very special properties which make it a material for the future. Despite being one atom thick, it is incredibly strong. The graphene can conduct electricity as efficiently as copper. The graphene is virtually transparent, yet is so dense that not even helium atoms, which are tiny, can pass through.
Folks, we're talking about when you're my age, thanks to this way of manipulating the way carbon atoms will bond to each other, when you're my age, you'll be able to see the computer screen on your glasses, on your contacts maybe. I mean, right now it's just science fiction movies. I think what, Mission Impossible and Bourne, whatever, they're conjecturing what they're already testing this. Okay? And this is why rich people are so important. Love rich people. Rich people are good. You know why? Because they have the money to buy these things when they first come out. And the more they buy them, the more they have to be produced. And the more they produce, the cheaper it gets. I am so old that I remember when VCRs came out. I had a friend. It was so cool. We would go to his house. His parents were loaded. And they had the VCR machine. It was huge, and we got to see movies. At the time, you could only see on TV or at the movie theater. Okay, and about 6-7 years later, my family could afford it. So, always love rich people. Rich people are good. And if you're rich, we love you. Buy expensive things. Bring down the price so that the rest of us can afford it. Let's look at the different types of chemical bonds. What are chemical bonds? The force that holds two or more atoms together. The force that holds two or more atoms together. What's going to determine how strongly the atoms are held together? Their bond energy. It's the energy required to break a bond. Question. Explosives, do they have a lot of bond energy or a little bond energy? You're absolutely right. Do you know why? Yeah, he's absolutely correct. Most people can't come up with that. Okay, in order for it to be an explosive, we need to be able to give it a little bit of energy and it goes boom. Okay? Exactly. The higher the bond energy, the more energy you have to put into it in order to split it up. That's why if you want to do something like carbon dioxide and you want to split it up, you want to use it as an explosive, it's not going to work. No fuse in the world will ever be enough to split carbon dioxide. Why? Because its bond energy is too great. So explosives are chemicals whose bond energy is not that big that we can give it a little bit of energy and it goes boom. What kind of bond forms between oppositely charged ions? This should be common sense. Ionic bonds. And of course, ionic bonds are when a metal gives its electrons to nonmetals. So metal plus nonmetal forms metal plus, nonmetal negative, an ionic bond. Here's an example, lithium and fluoride. One lithium, one fluoride, but as you can tell, it's not going to be one lithium, one fluoride. For every lithium you're going to have, it's going to be surrounded by fluorines. But for every fluorine you have, it's going to be surrounded by lithium. So if you were to count them up, it would be 1-to-1. Instead of saying lithium 5,365,232, fluorine 5,365,232, we just simplify and say LiF. Why? Because for every one Li, you have one F. That's how ionic compounds form. They create these crystals. Okay, this is NaCl. Is there one Na and one Cl in here? Oh no. There's quintillions, sextillions. Okay, but for every one Na, what? Yeah. For every one Na, there is a Cl. So we say it's just NaCl.
I see zombies in the distance there, but I also notice what looks like an ionic lattice, a sodium chloride ionic lattice, right in front of us. Notice the chloride ions that are negative are electrostatically attracted to the sodium ions, which are positive in this distinctive pattern. Now, ionic bonds are very strong, but if you add energy to them, you may weaken those bonds.
Okay, so he's adding bond energy. Bond
By
energy.
giving them more energy than the bond energy, and the ions may become free. And these freely moving ions have different properties, which we'll get into later. Alrighty, I'm getting a little scared the zombies are moving in, so I think I'm going to hop in my hovercraft and splat right through them. Those four there look good enough. Oh, you know what? Let's make this the PG version, which is Dukes of Hazzard straight over this bit here.
Isn't that funny that a Brit would know the Dukes of Hazzard? I mean, I wonder what these British people think of the South when they watch the Dukes of Hazzard. I know. My former pastor used to be a missionary to Italy, and he was there he lived in one of the big Italian cities, and they had a country music club where they would come, no, bluegrass, where they would come and they would all play bluegrass together, and all these Italians would show up with big old belt buckles and cowboy hats because they thought that's what Americans wore all the time. Well, I mean, Tom would show up in normal clothes and he goes, well, why aren't you dressed like an American? He goes, I am. No, Americans wear cowboy hats and big belt buckles. He goes, not where I'm from. And I'm from the South. So, what are the characteristics of ionic compounds? High melting point. Because they're so tightly bound together, such high bond energy, They have high melting points. They're closely packed together. They conduct electricity when dissolved in water or melting. All right. So let's come up with a metaphor to help us understand this. Freddie. No, we won't use. We've used Freddie so often, and we can't use Malachi because he's dating Maddie. We wouldn't want to embarrass him. What about Christian? You don't have a girlfriend, right? All right. So Christian. All right. So what if you were dating Betty White, 96-year-old Betty White? I wouldn't doubt it. So, Betty White, and we all know why you're dating Betty White, because she's rich. Okay, and you're hoping that you're still dating her when she dies, right? And that she leaves you some money. You gold digger. Christian, I'm ashamed of you. Okay, so she takes you to these Hollywood parties, and there you meet Summer Rae. Summer Rae. I've heard that I've seen a picture. I don't consider her to be that particularly attractive, but she is 22 years old, and yeah. Okay. So apparently Summer Rae is really close to your age and very good looking. So she's a supermodel. So Summer Rae comes up to you and immediately starts flirting with you. And she goes, "Are you dating anyone?" And you look back at Betty, who's entertaining somebody, and you say, "No." And Summer goes, "Would you like to date me?" And you look back at Betty and you realize, old, rich white woman, young, rich white woman. Yes, he says yes. So he goes to Betty and goes, "Hey, I'm transferring over to Summer. See ya." All right, so you are now dating Summer. Okay? So this goes on for a while, and then Summer comes up to you and says, "Hey, Christian, I am having so much fun with you. I was talking to Fall, my identical twin sister, identical twin sister, and Fall, and I was telling her about how cool you are and good looking and how sweet you are, and she would like to date you as well. So here are your choices. Hey, you can look at Fall and go, no, you're enough for me. I love you and only you. Or you can say, there's enough of me to go around. But since you asked me out first, I'd like to spend 5 days. I'll spend the weekdays with you, and then on the weekends, your identical sister, Fall. Okay? Or this is choice 3. You can say, you guys are identical. I can't tell you apart. So, hey, there's, more of me to love. How about 3.5 days for you and 3.5 days for your identical twin? Even Stevens. Okay? Which one do you choose? Even Stevens. Okay. Yes, Even Steven. Why? Because it's hard to tell them apart. Okay? So you spend equal time with fall and equal time with summer. All right. Third scenario. Ever since, Cass, are you dating anyone right now? Emma, are you dating anyone right now? Sammy, are you dating anyone right now? Okay, good. All right. Ever since the beginning of the year, you've noticed it. Okay? And you think she is so cute. And you've been in love with her until, of course, summer came and asked you out, and now you're in love with summer. But you still have this sweet spot for Sammy. So Sammy comes up to you and says, hey, I was dating this guy, but now I've called it quits, and I've heard that you're interested in me. How would you like to date? Now you've got choices again, Christian. You can date, you can go up to Sam and say, no, Summer's my gal. She's a supermodel, and you're not. Okay? Letter A. B, you can say, yes, Sammy, but I consider you to be just as good looking as Summer. So I will spend 3.5 days with her and 3.5 days with you. Fall's gone. Fall's gone. Fall got tired of you. She's gone. Okay. Or we can be realistic. Summer is a supermodel and she's rich. And as good looking as Sammy is, she's not supermodel or rich. So you can say, all right, 5 days with Summer, 2 days with you. You can share me unequally. Which one do you go? Which should I go for? Unequal share. Yes, good job. Unequal share. Sorry, Sammy. I mean, you're really really good looking, but you're not a rich supermodel. I know. I mean, it's just. Oh, okay, good. So you're not going to get mad at him. Okay, excellent, excellent. I have just described the 3 types of bonding. We've already looked at the first one, ionic. Which one of our scenarios was ionic bonding? If Christian is an electron, which one of our scenarios was ionic bonding? Yes. Yes. He did belong to Betty. Summer came around. Summer was better looking and younger, significantly, by 70 years. And she's almost as rich. Almost. But definitely younger. Okay? So what did he do? He transferred himself. The electron transferred from the element that wasn't as good looking to the element that was good looking. Okay? Now, let's look at the other 2 types of bonding. The first one is called nonpolar covalent bond. Covalent means sharing. Sharing is caring. And Christian, being a red-blooded American male, if given the choice of having 2 or more girlfriends, he will find a way to have 2 or more girlfriends. Christian, the hard part is making sure they don't find out that each other exists. Yeah, but I'm talking about, I'm giving you some real life advice here. Not that this has ever happened to me, but I have had friends who have tried. It never actually works. And then things get bad. Okay? But if you do decide to be shared, a nonpolar bond occurs if you're shared equally. If you're shared equally. So covalent means sharing, having more than one girlfriend. And nonpolar means being shared equally. What do we call it if it's unequal sharing? Polar covalent. Okay, this is an example, a visual representation of nonpolar. What do we have here? We've got summer and fall. The little green dots represent Christian. Notice where most of the green dots going to be. right in the middle, evenly distributed, right in the middle. Why? Because he couldn't decide. They were identical. So what happens is the electron cloud is evenly distributed. There's not more electrons on one side than there is on the other. Okay? But what about this situation? This is Sam, and the F is Summer. Who's richer? Who's more popular? Summer. So what do we find? Since Christian is so shallow, we find that Christian is mostly around fluorine. Not that he's going to give up on Sam, because after all, he's been in love with Sam for a long time. You know, Summer is a recent thing. But sorry, Sam, Summer is richer and more popular. That's true. That's true. You're a very open-minded young lady. I applaud you for that. Okay, so what happens when you consider that every little pink dot is a negative particle? Where are most of the negative particles? Around the F, right? Here, where was most of the negative particles? In between, not one side or the other. But when the difference is significant, then what we find is that the electrons are going to be around the more famous one, giving it a negative pole, a negative sign. That's why we call it polar, because it has a negative side, and Sammy represents the positive. The negative side and the positive side.
The most important of those classifications is whether a molecule is polar or nonpolar. It's a kind of symmetry, not just of the molecule, but of the charge. It's pretty easy to see when you're just looking at them. You got polar and nonpolar, polar, nonpolar, polar, nonpolar. I'm going to take sides right now. I'm on team polar. I think polar molecules are way more interesting despite their wonky off-balance selves. Nonpolar molecules are useful and their symmetry has a kind of beauty, but polar, in my humble opinion, is where it's at. Alright, now here are two very different types of chemicals. Right here I have a stick of butter, and then in this bowl, that's just normal water. So I'm just going to go ahead and squeeze this butter, which if you're wondering is both a terrible and wonderful feeling. And then I'm going to just drop that. Now I'm going to attempt to wash that butter off my hand, but that is just not it's not going anywhere ever. It's just beating up on me. Why? Because water is a polar molecule and the various chemicals that make up butter are nonpolar, and water wants nothing to do with that. Ugh. So, what makes a molecule polar? Well, two things. First, asymmetrical electron distribution around the molecule. You can't have a polar molecule made up entirely of the same element because those atoms will all have the same electronegativity, and thus the electron distribution would be completely symmetrical. Electronegativity is usually thought of as how much an element wants electrons around it, but I think it's more about how much electrons want to be near that element. If electrons were 13-year-old girls, fluorine would be Niall Horan. They'll do anything just to be near it. Liquids made up of polar molecules are really good at dissolving solids that are composed of polar or ionic compounds. Ionic solids are basically just polarity taken to the extreme, so far that instead of having a partial positive and partial negative dipole moment, the electrons have completely transferred, creating two charged ions. Now, I assume we've all heard that like dissolves like, so the easiest way to figure out if a liquid is polar or nonpolar is just to dump it in some water. But the why of this phenomenon is usually just totally glossed over. What's actually happening to those molecules? It seems like they're all just bigots, terrified of anything even a little bit different than themselves. But this is chemistry, so there must be some fundamental reason, and if it's fundamental, it probably has something to do with decreasing the energy of the system. And indeed it does. Those partial positive and partial negative charges of water, they're at their lowest energy state when they're lining up together, positive to negative, into a kind of liquid crystal. There's an arrangement there. It flows, of course, but the oxygen sides are always doing their best to orient themselves toward toward the hydrogen sides of other molecules. You can even see the effects of that attraction as the surface tension that allows me to pour more than 100 milliliters of water into a 100 ml container. The strength of that surface tension depends on the intermolecular forces that pull molecules of a liquid together. These attractive, also called cohesive forces, pull the surface molecules inward. And what you see when you look at this pile of water is the result of those cohesive forces, minimized surface area in the water in this beaker. When you put a bit of oil into that mix, the water totally freaks out. Oils have notoriously nonpolar molecules, so suddenly there's this mess of uncharged gunk interfering with the nice orderly arrangement of polar water molecules. But if you take a closer look, the processes are very similar to those between water and air. Water does everything it can to minimize its surface area and kind of expels the oil droplets. Rather than the water disliking the oil, it actually just likes itself much more, so it won't mix with the oil. Now if you put polar stuff in, water's all about that, and those polar water molecules just go after whatever other partial charges they can find. Or in the case of many ionic solids, the partial negative charges on the oxygen side all gang up on the positive ions, while the partial positives on the hydrogen side surround the negative ions, breaking the crystals apart and dissolving them into freely moving ions. In some cases, we can actually witness these interactions in unexpected ways. Mix 50 milliliters of water with 50 mils of alcohol, and what the heck, there's less than 100 mils of liquid. The arrangement of water mixed with alcohol is actually more structured and thus more dense, resulting in a smaller volume. And amazingly, we haven't even finished talking about how powerfully useful these partial charges are. They also allow water to dissolve pretty much anything that's even partially nonpolar, which includes sugars, proteins, ions, and tons of inorganic chemicals. Water and its useful little dipole moment can dissolve more compounds than any other chemical on Earth. Frankly, it's amazing that it doesn't dissolve us from the inside out. Which brings me to one little last polarity tidbit, the hybrid molecule. There are lots of molecules, like the surfactants in soap, for example, that have both polar and nonpolar areas. Dish soap is thus able to dissolve the fatty parts of my butter catastrophe here, and then stick the polar sides out, allowing the whole mess to get washed away by Avogadro's numbers of polar water molecules that I'm sticking on my hand right now. Oh yeah, that's better. But not, I'm going to have to go to the bathroom to get this all the way fixed up, so be right back. Likewise, the fatty acids that make up your cell membranes have polar heads, which keeps them interacting with the aqueous environment of our bodies, but nonpolar tails, which prevent the cells from just being dissolved by the water around them. Pretty dang elegant, if you ask me.
All right, let's stop it right there and continue tomorrow.